here. In this video, we are going to go over angled forces. In the previous videos, we went over how to draw a free body diagram for angled surfaces, but for this video, we are going to apply some math along with some trig. So make sure you have your calculators nearby. You'll definitely want to know how to use your calculator for this portion of physics. So let's begin. The first scenario here, you see on your screen, take the time to pause the video and copy this down. Mr. Lee drags a box across a surface with constant velocity. He pulls at an angle of 30 degrees with a force of 200 newtons. The box has a mass of 30 kilograms. All right, so that's the scenario. Pretty standard scenario. You'll come across problems like this, so it really does help if you copy these down because you will definitely see in the future, trust me. So the first thing that I want to do is, of course, the interaction diagram. I find that they are extremely helpful, and I hope you do too. So our focus here is on the box, and we have Mr. Lee, we have the earth, we have a rope, and we have the surface. So in case you're wondering how I came up with this, it always helps to have a little sketch. So I'll just do a quick little sketch right here. I have a little box right there. This is the rope that is being pulled, and this is, I guess, I don't know. How am I pulling this? There we go. All right. So I'm trying my best here. All right. So if I have an interaction diagram and I come up with my forces, let's do this. So the rope is touching the box. So we can call this the force of tension on the box. The box is touching the surface. Okay. So we definitely have a normal force on the box, as well as a possible force of friction on the box. Remember, if you are moving with constant velocity, there's a high chance that that you have a force of friction if you're dragging an object. Otherwise, the object will accelerate. Okay, the earth in the box, this is what we call the force of gravity on the box, also known as the weight. I think that might be it. All right, very good. So I just wanted to point out that here I am not touching the box, so I am not drawing a force on me on the box. Okay, the rope is touching the box. Okay, so here's my sketch. Here's my interaction diagram. So let's actually come up with the free body diagram. So on your FRQs, if they ask for a free body diagram, the only thing that you can put on there are actual forces. No components, but the component portion helps you with the mathematics. Okay, so what I like to do is I like to insert the FRQ directly and just have a free body diagram off on the side that I can do that I can use for math. Right, so let's go over these forces one by one. So we should have a total of 1, 2, 3, 4 forces. Okay, I'm dragging this box to the right, and our acceleration is 0. And the reason we know this is because we're moving with constant velocity. Okay, so yeah, all my students know that if we have constant velocity, all of the forces should have a pair that cancels them out. So the very first force that I want to draw is the force of gravity going down. Okay, now I want you to be in a good habit. If you have the force of gravity right next to it, mg, okay, that's just a good habit for you to do because it's a way for you to quickly realize what the formula is for the force of gravity, also known as the weight. By the way, this is the box. All right, and then we have the normal force here, F of n on the box. Okay, and we have the rope being pulled at the angle, so we have F of T on the box. And we have a force of friction here, F of F on the box. Now, what I like to do is I like to put it in a little theta. Okay, that's the angle. And for this problem, it's 30 degrees. All right, that's not necessary for the free body diagram, but it sure does help. All right, so for FRQ, if you're looking for free body diagram, that is all you have to submit. Nothing more, nothing less. I do want to put a little note here. Note, no equivalent forces notation. Okay, you might want to make the normal force and the force of gravity equal to each other, but we will soon see mathematically that is not the case. Okay, so this is a big note. This is very important. This situation comes up a lot. Okay, one thing you'll notice that in physics, the problems and situations, they're all basically the same. One day you're pulling a box, another day you're pulling a sled. One day there's friction, another day there's no friction, right? The situation is basically always going to be the same. The situation is. All right, so now that we have a free body diagram, what we can do now is create a free body diagram, but with components. And once again, it's a component version that helps us out with the math. So let's just quickly sketch one of those out. Okay, we have f of g equals mg. So here what I'm going to do is I'm actually going to write in my values. So we know that the mass of the box according to the problem was 30 kilograms. So I'm going to put in 30 times 10. So this gives us 300 newtons downwards. So mathematically that'll be negative. You can write in negative there if you want. I'm just going to save space and not do it. I usually do, but that arrowhead down helps me out. All right, and then we have f of n going up. We didn't calculate that yet. All right, so I'm not gonna write anything there. We have the force of tension on the box going up at an angle, and we have, of course, this 30-degree angle, and we have this force of friction right there on the box. Okay, so after you do that, I'm going to get a different colored pen, and I highly, strongly, like this is, you cannot go wrong if you use a different color on this. Okay, so while we're in the practice mode of it and not actually taking the test, get a different colored pen because it will help you out. So if I take a look here, my x and my y-axis. Okay, so this is my x-axis. And my x-axis is usually parallel. So let's write that there. X-axis is parallel to surface. Okay, and the y-axis is perpendicular. So that's a symbol for perpendicular to surface. I don't know about you, but if I were in a spelling bee and the word was perpendicular, I will surely be eliminated. So I'm going to use a symbol there. Okay, so the y-axis is perpendicular to the surface. So this is my y-axis. So any force that is not along this y or this x-axis is a angled force. Another way of knowing that is, well, the angled forces have angles attached to them. Okay, but just in case you're not quite sure, I'm going to get a highlighter real quick. I'm going to highlight all of my y-axis in yellow. So these are my y-axis. Okay, and I'll do the other one in, let's do a nice little green here. This is my x-axis. So you can see here that the only force that has not been highlighted is my tension force. So what I'm going to do with a different color is I'm going to break this apart. Okay, so if I were to ask you, this force of tension, okay, this arrow, what direction is it pointing? So we would write F of T is pulling. Remember, ropes can only pull up, very important, and right. All right, so the reason why it's important to notice this is because when you draw your components, and this is a part where a lot of students mess up, they don't actually draw in the arrowheads correctly. The arrowheads, you need one arrowhead pointing upwards, and you need one arrowhead pointing to the right. So I'm going to draw that right now. I'm going to draw the one to the right first. So we have the arrowhead pointing to the right, and we're going to call this F of T X, because that's along the x-axis. And I'm going to get another pen, and we're going to call this one F of T Y. All right, so a quick little pointing out right here. My arrowhead is pointing up, right? And I have another arrowhead here that is pointing to the right. I have one going upwards and one going to the right. If you do not have those arrowheads, it'll mess you up mathematically, and also your points can be definitely taken off because you're not fully understanding the components of this force. So the components are describing what that force is actually doing, and the rope is pulling on the object upwards and to the right. Okay, so here we have our component forces. I'm also going to write down next to it the formula. So this is where the trick comes in. You see this angle here, this 30 degrees. Okay, that 30 degrees is touching this FTX. So because it's touching, this is a adjacent force. And so we can write this as F of T. And if you remember the previous video, I went over the SOHCAHTOA. Adjacent always uses cosine. So this is force of tension, okay, whatever that value might be, times the cosine of the angle. And in our case, that will be 30 degrees. All right, so this FTY is opposite, okay? It is opposite of this angle. So because it is opposite, we have to use the sine function. So this would be Ft sine of theta, okay? Now, we can actually plug our numbers in. I'm going to plug in my numbers over here where I have a little bit more space, okay, so that we can see what each one of those values is equal to. So Fty is equal to F of t sine of theta. And we know that F of t, I believe it is the 300? 200. All right. So I pull to the right with a force of 200 newtons. Okay. And sine of 30 degrees. And this is where your calculator comes in. If you put in sine of 30 degrees, you should get 0.5. Now, if you don't, it's because you're in radian mode and you can change it. You have to be in degree mode. Let's write that there. You have to be in degree mode. Chances are you're in radian mode if you use the calculator in math class and you're doing the radian stuff. But for us in physics, we always have to be in degree mode. Okay, it's very important. All right, so sine of 30 should give you 0.5 times 200, and so that will be an answer of 100 newtons, and right here up. Okay, because that's the arrowhead that's pointing. All right, now let's do one for Ftx. So here we have Ftx is equal to F of T cosine of the angle. And our F of T is 200 cosine of 30. So I'm going to type in cosine of 30. So if you're following along, and I hope you do, because you have to get used to using your calculators, you should get 0.866 and some numbers after times 200. And I get 173.21. I'm rounding to 2 decimal points newtons, and this is to the right. All right, so we have our two forces, okay? Now, with this component version, here, this is where we can come up with our equivalent forces, okay? So if I take a look along my x-axis, there's only one other force that is going against Ftx, and that's the force of friction, right? And so that must mean because our acceleration is equal to 0, all the forces have to cancel out. So if I have Ftx going to the right of 173 newtons, the force of friction on the box is also 173.2 newtons, except it's going to the left. All right. So what I'm going to do is I'm going to redraw this so that I can now put in the numbers. Right. I have my work. It's all here. It's a little bit messy. So I'm going to redraw this so that I can fill in all the values that we found. All right. So we found that our F of G, I'm not going to go through the whole math, is 300 newtons. We have our F of T, and our F of T is 200 newtons. We have our F of F. Okay, I'm not going to do that just yet so I can show you how the math works out. And we have our F of N. All right, we found that our Ftx is equal to 173.21 newtons. Okay, and we found our Fty to be 100 newtons. All right, so if I look at the x-axis, I know that my force of friction and my Ftx, they have to cancel out because those are the only two forces along the x-axis. So that must mean that this force of friction is 173.21 newtons, but to the left. Okay? All right. Now, if I take a look at my y-axis or my vertical axis, I see F of n going up. Okay, and I see Fty is equal to 100, and I see going down, I have F of G of 300. So what this means is that all the forces have to add up to 0. So if my F of G is 300 going down, my FTY is 100 going up. That means my surface force, my normal force, isn't pushing back with 300, but rather 200 newtons upwards, because 200 plus 100 gives us 300, and 300 up plus 300 down, this gives us 0. And the reason why we're chasing these zeros is because our acceleration is 0 meters per second squared, because we're not speeding up or slowing down. We're moving with constant velocity. So what that tells us is that all the forces have to add up to 0, because remember, the free body diagram, the force body diagram, it does not show us motion. It shows us the forces and the acceleration. Very good. All right, so I'm going to plug that in here. And ta-da, we did it. Okay, you found all the values for the forces. Good on you. All right, so let's do another one. Now let's do one where we have an object on a slanted surface. All right, so we have an object here on a slanted surface. And we'll have the same box, right? So we'll say the box has a mass of 30 kilograms, and we will say, let's say the box is sliding down and to the left, and our acceleration is 0. So this is down and left. Okay, and acceleration is still 0. All right, so if I were to come up with a free body diagram, okay, our free body diagram from before, it doesn't change except our axes are different. Remember, our x-axis is parallel to the surface, so this is x, and our y-axis is perpendicular to the surface. This is y. Once again, I highly strongly suggest that you always write in your x and your y axis and get used to it, because that is half the problem right there. All right, our interaction diagram, that's not any different. The only thing that's different is that there's no more rope. Okay, I got rid of the rope. So if I got rid of the rope, that means we only have F of G, we have force of friction, and we have the normal force. All right, so let's do F of G first, going straight down. I like to draw my force of gravity a little bit longer because it helps me when I'm like writing stuff in. It gives me a little bit more room, but I'm going to redraw this again, so you don't have to worry too much about that. And we have our normal force perpendicular. So this is where it's helpful, where you identify the perpendicularness. And I just draw a little 90 degrees right there to remind myself that's a perpendicular force. Okay, now, and it wants to, it's moving down the ramp, down and to the left, so the force of friction always goes against that motion. So the force of friction is up and to the right, just like that. All right, so this is my free body diagram. You submit that, you get 100% on your FRQ, you're happy. But now here comes the tricky part, the actual math. All right, so before we do the actual math, I'm going to draw the free body diagram again. I'm going to make it nice and big. And I highly suggest that you, when you do this math, you use up as much paper as possible, because when you do this work and it's nice and tiny, that's when things get complicated. Okay, it really helps so that when you're looking at this, you're seeing it in a nice big view. All right, so I'm going to draw the force of gravity going down. Oh, I almost forgot. I need to label my x and my y axis. Okay, I don't want to be caught not doing that, and you don't want to be caught not doing that either. All right, and so we have the normal force going up. All right, and it's perpendicular to the surface, and we have the force of friction like so. All right, and our velocity is down and left of the ramp, so it kind of looks like that, and our acceleration is 0 meters per second squared. So this tells us that all of our forces need to cancel out and add up to a value of 0. All right, so the component portion, this is where things get a little bit tough. Our y-axis has now changed. So before, up here in this problem, our F of G was along the y-axis, right? You see that. But here our F of G is no longer along the y-axis. And how do I know that? Well, here, I drew my y-axis over here, right? I'm going to see that my y-axis is no longer along the perpendicular to the surface. Oh, I forgot. Let's put an angle there. Let's just call this 30 degrees so it matches the other problem. Okay, so here we have our situation here. And what I want to do is I'm going to come up with the components. So this is where the students mess up the most, okay? And wherever you are in your notes, get a highlighter, get something right nice and big, because this is what will separate you from a great problem experience from a bad problem experience. This portion right here, drawing in the components for a surface force that is angled. All right, or a force of gravity force that is angled. So what you want to do is you want to make sure that your forces line up with your y-axis and your x-axis. Okay, it has to line up. So I'm going to draw my y-axis first. The y-axis one is a little bit easy. I just go down a little bit. Okay, dotted lines because they're not real forces. Okay, I'm going to stop right around here and you'll see why. Now, if you go a little bit beyond, that's fine, okay? But your x-axis has to be parallel with your surface. So here's my surface, okay? My surface is this green highlighted portion right here. It has to be parallel to that surface, like so. All right, so that is how you draw FG of X. All right. And right here, I'm going to draw in my arrowhead because this is my FG of Y. So if I were to ask you, what is your F of G doing? Okay, your F of G is doing two things. Thing one, so FGX is, so the force of gravity is sliding or pulling the box down the ramp. Down the ramp. And what I mean by down the ramp, I mean in that direction, okay? And so that's what this is telling you. The force of gravity is sliding / pulling the box down the ramp. And FGY, what is FGY doing? It's doing the same thing that it was doing in the previous problem. So here, in the previous problem, if I were to ask you, what is FG doing, or FGY, remember FG here is along the y-axis. So what is this FG doing? You can say the force of gravity is pulling the box against the surface. Okay, and so the situation is same here. FGY in this situation is pulling the box against the surface. Okay, that way the box doesn't fly off the ramp or it's not digging into the ramp. It is just along the ramp. It's pulling the box against the surface, but FGX is sliding the box down the surface or down the ramp. All right, so here's how you know that you did it correctly. You see where these two components they connect? That should be 90 degrees. Right? So as you draw your triangle, if that does not look like 90 degrees, then you drew your components incorrectly. Now don't try to fudge it and don't try to put the 90 degrees elsewhere. Your 90 degrees is between your two components and it needs to belong there. Okay? And it's the only way that you know if you actually drew this correctly or not. Right? And then once again, it comes with practice. So here we have a 30-degree angle, and this angle here is also 30 degrees. Thank you, trigonometry and geometry. The proofs is in the numbers right there. All right, so let's come up with the values. FGY, I'm just going to do the math right there. Okay, FGY is just F of G, which we found to be 300, I believe, from the previous problem. Remember, the weight of the box did not change. Yes, it's 300. All right, so that's F of G. And if we take a look here, right, this side of the triangle is touching this angle right here. So because it's touching, it's adjacent. So this is cosine of the angle. Okay, so if I plug that in, we get 300 times cosine of 30. And I hope you're doing this along with me. That should give you 0.866. So 0.866. 300 times that gives you 2259.81 newtons. Okay, and FGX here, FG, oops, I was about to say cosine, but here we see if this is our angle right here, FGX is opposite of that. It's not touching it, so this is sine of the angle. So we have 300 sine of 30, and that should give us 150. 0.5, 150. So I hope you're following along and you're getting used to the trig functions on your calculator. Yeah, because you'll be asked to do that in class and on your exams. All right, so here we have our two forces. All right. Okay. So with this, now we can figure out the rest of the forces. Remember, this FGY, okay, if I were to ask you what's FGY doing, you should be now able to say is pulling the box against the surface. Key word here, surface. Remember, the normal force is a reactionary force, okay, of what the surface is doing because there's a force acting against it. If you push against the surface, it doesn't matter if it's the floor or if it's the wall, that surface will always push back. So if the force of gravity is pulling this object against the surface with 259.81 newtons, the normal force will be opposite of that. So 259.81 newtons. And I'm going to draw my equal force symbols. Okay, they're equal but opposite there. All right. Now, what about this force of friction? Okay, so this force of gravity is sliding this box down the ramp. Okay, but it's moving with a constant velocity, and the acceleration is 0. And what's this force of friction doing? It wants to prevent it. Okay, so because the forces have to be equal, okay, if the force of gravity is pulling it down the ramp with a force of 150, that means the force of friction is also going to be 150 newtons. Oh yeah, looking good. So let's do one thing I forgot, we should do equivalent forces. Remember, equivalent forces come in pairs, so this 150 is equal to this force right there. All right, so we have two pairs of forces. We have the normal force and FGY, and the force of friction and FGX. Will that always be the case? No, it was just the case for our problem here. And it's very important for you to identify the equal forces, because remember, in physics, we're always chasing those zeros. All right, and we found all the forces, and that's that. Ta-da! The only thing that was left for us to do is to practice. So we're going to practice. I'll see you next time. Bye-bye.